morning, everyone. I think we can start. It's my great pleasure to have you all back after every month. It's nice to see you again and to see new faces as well. As I always mention, this is really an opportunity for the CIBM community to get together and learn and find out more and to ask questions and really to mingle. But with the circumstances, mingling is a little bit virtual, but nevertheless, it's working. Okay. So it is my great pleasure now to introduce Eleonora Fornari, who's been in CIBM for a very long time because she's had this 10-year collaboration, as it says here, since 2006, I believe, Eleonora. So Eleonora is a research staff scientist at the CIBM MRI CHUV-UNIL Section, and she'll be sharing with us the journey through 10-year collaboration on prismatic adaptation. Thank you, Eleonora.
Thank you, Pina, for letting me presenting this journey. Exactly, it is a way to acknowledge. It is a bit different presentation than what the ones that we are used to, but it was important for me at this time just to acknowledge this collaboration that started with a small project about 10 years ago, and it does not stop, and I'm very happy of that. This is an example I wanted to share with you, an example how a small personal project can become a fruitful and long-lasting collaboration, even though it is local. So that is my purpose today. So for me, it was important just to start my presentation with this sentence of Henry Ford that is coming together is the beginning, keeping together is progress, and working together is success. I couldn't find a better note of that explained how do I feel to be a part of this project since the beginning. For what I can see, I mean, the project in general, any kind of project, at least in our domain, should have 4 pillars. Of course, a scientific impact that comes from a clinical question most of the time. I mean, that is our purpose, but has to include also a very important part of training and knowledge transfer and collaboration. I just apologize for the icon that is not COVID-19 compatible, but I couldn't find anyone with the elbows, so sorry about that. So let's start. I started the presentation in the opposite way, so I started sharing with you the training and the collaborative impact of this project. It started exactly 10 years ago with a small fellowship of Maritime Berkeley Fellowship, and it started within the Neuropsychological and Neurorehabilitation Department and the CIBM together with the radiology service. But now it is growing, even though since it is still local, but it's growing. There are either companies or teaching and other hospital and other labs that bring also to the CIBM that they have brought, I mean, in the last years, new collaboration and new project within our section. So let me thank first to the team. So Sonia Crota-Herbet, she was the one who initiated the project with her fellowship. And she came to me 10 years ago and say, oh, I have a small project, but I have an idea, a good idea. And then she was supported by the professor, the head of the neuropsychology and neurorehabilitation, that then continued with other fundings, this project and develop it. And together with Sonia, they could develop a very complete project. Within this project also there was one PhD in neuroscience, Isabelle, and one MD, Louis, who work on that. But not only that, but 14 master students in medicine and biology, they worked within this project. So let me just give you some numbers. There were about 300 hours of MRI acquisition. So we are talking about brain MRI acquisition. 1,000 or nearly infinite hours from when you look back our hours of data processing. There were 2 or 3 trained persons at MRI scanning, in the sense that there were 3 persons, but one of them was trained within another project. And of these 2 new trained persons for this project, one is now, has moved to another lab. So she's scanning for, another lab. So they are independent as well. There were more than 10 trained people at MRI data analysis, and more than 10 trained person at cognitive intervention neuropsychological testing. So even though it is a small project, it is an example of training and knowledge transfer and care about, students and the following scientific, the transfer of scientific knowledge for the new generation of research stuff. All these persons worked very hard, and it came out of this project. Did 7 peer-reviewed papers, more than 20 conference presentations. The PI made also 2 reviews. And so now it is time just to go through exactly this journey of through this scientific and clinical impact. So a research question comes out as often from a clinical evidence. And in this case, it was concerning patients with right hemisphere damage and showing unilateral neglect. But what is unilateral neglect? It is characterized by the inattention to stimuli that are presented contralaterally to the brain lesion. This neglect, unfortunately, is persistent in a significant percentage of patients and associated with poor functional outcome. In most cases, like as you can see here, the right hemisphere damage causes inattention for the left hemispace. So you can see that a patient who has a unilateral neglect, it will recopy just a picture just on the right, the right part, because he has inattention on the left side of the visual space. Since rehabilitation is still in development, either with top-down or bottom-up approaches, the project was aimed at the beginning at verifying the incidence at the neural substrate of an intervention that is prismatic adaptation. But let's see what is prismatic adaptation. It consists in wearing prismatic glasses, which deviate the visual field. This induces unilaterally during the first trials pointing errors that after a certain time of training are adjusted. So, and this after effect compensate for the visual discrepancy, visual motor discrepancy induced by the prism. So in this case, I will show you what is does it work like that? Yes, okay.
Close your eyes.
This is a pre-PA, so even with eye closed, the subject can point more or less precisely, the point. Then he wears glasses.
And now you have to do very quick movements, okay? Go to the right.
Okay, this is the first after effect. So
To the left.
you can see, and then after a while, okay, after a while, you can readjust the sensory motor coordinates to
Go back to the start position.
to hit the target. But what happens when you remove them?
Look at the dots. Close your eyes, point to it.
Okay, so we have an after effect in the other
Go
direction.
back to the same position. Look at this dot. Close your eyes and go for it. Good. Look at your finger.
And actually, it is more often more evident into the left hemispace in this case. So, how this prismatic adaptation can help unilateral neglected patients? Because it can help them because the rightward optical shift can help people to improve the left hemifield representation, at least for a few hours. I mean, a single session of prismatic adaptation, just between 5 and 10 minutes, can improve the left for a few hours. And it has been shown that after 2 weeks of daily session, this improvement can last up to 6 months. What has been done in this project? So, I mean, more than testing the neuropsychological, the testing and the effect. So it was done by FMRI. So every experiment was a pre-post experiment with a training in between. So the FMRI was a visual detection task, a very simple visual detection task. A star was presented either in the left, in the center, or in the right hemifield. And the subject had to respond as soon as possible just by pressing a button. So the resting state, this task was presented before and after PRISM after the post prismatic adaptation was always done within 30 minutes after the prismatic adaptation to be in any case in the first phase after the adaptation. And all the subject went also through our resting state fMRI at the same time, and then anatomically and DSI divided in the first and the last just to balance the two acquisition time. So what are the results? So they started with control subjects long time ago. So what has been shown is that, just to test what happens with prismatic adaptation in controls. So what has been seen is that even a brief exposure to rightward prismatic lenses modulates the representation of the visual space in the inferior parietal lobule and in the inferior parietal or the left angular gyrus more precisely, and decrease the representation in the left visual field, and decrease the representation of the right and the central visual field within the right interparietals, the right supramarginal gyrus. Thus, in normal subject, it can be seen that the rightward prismatic adaptation changes hemispheric dominance of visual spatial representation within the ventral attention system. These two regions become from the they are part of the ventral attention system divided by the ventral and the dorsal. But they are part of the ventral attention system. And this adaptation changes the dominance of the visual spatial representation within the ventral attention system in favor of the left hemispheric competence. And this effect is not related to a test-retest because it has been tested with subject, also with control subject that did not went through a prismatic adaptation. So, and also depend on stimulus position. So in the left the left stimuli are much more let's say that the effect can be more seen in the left than in the center or in the right, the effect of prism before and after. So since not only because of good side, but we have to admit that it was also reviewers who asked. So they ask also, but what about if we deviate in the other direction? So the other direction for the completing the assessment of the also leftward prism were tested. In this case, the left prism adaptation enhanced the right hemispheric dominance, so it is like a mirroring. However, the effect is less intense, probably due to a plateau in the right hemisphere that is already highly engaged in global attention system. Next step, so was to see the interest was also in the supramodal effect. Following these results, it has been tested the possible supramodal effect of prismatic adaptation. What is supramodal effect? It is the interaction between a modality, the effect of visual prismatic adaptation on stimuli that are not necessarily visual. But since the attention system is generally engaged in every kind of sensory motor control, it was highly probable that, even a visual intervention could help or could have an effect on another modality. So this was done with the visual, exactly. They tested with visual prismatic adaptation and detection of auditory stimuli. These stimuli were located as the visual one in the left, center, or the right hemispace. The normal subject went again to a small adaptation. And what has been seen is that in either modality, the representation of the left, center, and right space increase in the left intraparietal lobule or angular gyrus, and decrease in the right. So thus a brief exposure modulates to prism, modulates the representation not only of the visual, but also of the auditory cortex and auditory and visual space within the ventral attention system, exactly towards the left competence of the hemisphere. Then, this has been done at the end, but I present here since it is very recent. It has been done just during our not lockdown. We didn't have a real lockdown, but it was just revised and published early in 2020. But it is a resting state FMRI connectivity study on this data, but on control subjects. So the whole brain, it was done first a whole brain analysis, a mixed structural and functional connectivity that showed some, nodes and connection and nodes and edges that show an interaction between the time point and the group. It has been done on two control groups, one that underwent the session, the prismatic adaptation session, also before and after. So it went to the adaptation, they were scanned before and after, and another control group who did not, who had no intervention at all. But we are speaking about controls again. And it has been done that there are some regions that show a difference in connectivity through the connectivity matrices. And what has been shown that inferior frontal, inferior front and inferior temporal, they are part of the dorsal of the ventral attention system. So also the interest was just to check the connectivity strength within the specific networks that were more interesting. So the ventral attention system and the dorsal attention system. If these two networks are more than the whole brain analysis. I mean, a local network analysis has been done, and it has been seen that even though global efficiency, there are no differences between pre and post, neither in the ventral attention system or the dorsal attention system networks. There is, in any case, some differences between the post in the connectivity strength, between pre and post, and between the post in the two groups, and the local efficiency. So since the local efficiency is a measure of information exchange at a local level, it has been seen that a brief exposure, I mean, it is the results have been completed by showing that the brief exposure changes its resting state connectivity and decrease at least the local efficiencies of information exchange within at least mainly within the ventral attention system, and this is not seen in the dorsal attention system. Let's go back after having all the results about controls. But what happens in patient? That was the primary objective of the project, to see if this adaptation can, what are the neural substrates of prismatic adaptation in patient with the right hemisphere damage at the beginning. So 15 patients, and here you can see the overlap of the lesions. Not all of them had this lesion, but this is just the overlap. Underwent exactly the same visual spatial attention task. And what has been seen is that compared to control subject, where in any case, the accuracy was always at a plateau level, because the accuracy, I mean, whatever you present to a subject, I mean, they can detect, I mean, in the visual spatial attention task. But what was interesting is that the accuracy of patients that could not really see, I mean, sometimes they could not see the targets in the left hemispace, of course, they increase the accuracy, but it is more evident in the left hemifield, and they decrease the reaction time thanks to the prismatic adaptation. And what happens then in the brain? So across patient, so we have a similar, of course, we have similar results than in subject, except that the fact they do not have the right part of the brain that is available. So, but what happens is that across patients, the increase in neural activation within the temporal regions, also within these temporal regions, correlates with the performance improvement in the visual space. If in the control subjects, prismatic adaptation enhanced the representation of the left visual space within the left inferior parietal lobule, in patient we have the same, but the region extended beyond the inferior parietal lobule to the temporal convexity. And this result suggests that the left hemisphere provides compensatory mechanism by neglect, by taking the representation of the whole space within the ventral attentional system that usually is predominant in the right hemisphere. So that was very important. You can see that both in the left anterior superior temporal gyrus and the left posterior superior temporal gyrus, we have a significant change in the left position where they recover a certain attention capacity into the left position of the left position of the stimuli. So the conclusion of all these studies is that there is a model. I mean, the normal, it has been to make a model, I mean, of course, to explain how to explain this, all these effects. What is usually the ventral attention system that takes the responsibility of takes the responsibility to make make a whole of your visual input. If it is damaged, can be recovered by, I mean, a shift, an intentional shift over the left regions that can take, I mean, they can take a compensatory effect within the ventral attention system, and thus then passing through the dorsal attention system that still can connect maybe by spare callosal connections. But where we are, I mean, all this, it has been seen under all the possible, the effect of prismatic adaptation has been seen under all the possible angles. But the problem is that it is evident that not all neglect patients respond equally well to prismatic adaptation. So there are some current challenges that includes the identification of what are the indications for using prismatic adaptation on a certain patient, not on the others. So to define the profiles of patients who could respond not only to prismatic adaptation, but in general to any kind of cognitive treatment, or and also to understand the mechanism underlying the effect. And the group is really believe that neuroimaging can provide can provide biomarker with prognostic values of any kind of therapy, cognitive therapy, and help to individualize the treatment. But then what is next? I mean, is it done? They have seen everything from all the angles, but no, it is not done. It is not done. We are still continuing. What's next? They want to use virtual reality. Why to change to virtual reality? Because it helps, it can simulate everyday situation better than just a simple visual task. So the aim is to enhance therapy's efficacy, maybe, or to assess more complex spatial cognition tasks required in everyday life. So what is the point of using prismatic adaptation plus in virtual reality? I mean, or in virtual reality, it is that we can see virtual reality as a therapeutic tool, so use it just for virtual prismatic adaptation, or also to assess if VR can be, to use virtual reality as an assessment tool. So does, for example, prismatic adaptation modulate perception in virtual reality? So this is the new that are being done in collaboration with a MySpace lab. There it is ongoing, and with this I end with what I feel totally true of this collaboration, because it is a personal. It is something that, I mean, I feel it strongly. I'm very proud of being within this group since the start, because I really feel that a team is not a group of people who work together, but a team is a group of people who trust each other. And that is really what I feel. And I would like to thank all these collaborators for these wonderful years. So thank you really for your attention, and I'm available for a question, and there should be also Sonia, who is online.
Okay, thank you, Eleonora. Fantastic. It comes at a great time because, as you all know, last year we were celebrating the 15th anniversary. And so this really shows an example of the work that has been done over the years and all the achievements. So are there any questions for the audience? From the audience?
Hello, I'm Mary. I have a quick Tawele.
Ciao.
For this very inspiring talk. I really like it and how you present it and you swap the regular traditional presentation styles. A very specific question on the image processing side. So if I understood well, you had a group of patients that had these lesions quite consistently located on the right hemisphere. And I was wondering, actually, when you have to do your analysis on resting state or task, whatever driven, you need to put them in the same space. And I was wondering, yeah, how you deal with all this. So if there was variability or not in the size and location of the lesions, and if you faced problems in actually putting them together, how did you deal with that?
I remember perfectly. It was in 2015. So actually, I mean, the lesion of the patients were quite different. I mean, what I showed it is just the overlap, the maximum overlap of all the lesions. And in this case, all the lesions, all the voxels that were at least present in one lesion were removed from the analysis. In terms of, that is why, because so far it is not possible. I mean, it is very complicated to manage the degrees of freedom of your model according to the number of subjects that is variable. So if one voxel has just the data from one subject or two subjects, for example, if this lesion, if one voxel is present in several patients, in few patients and not in the others, you have a problem in managing, I mean, exactly, and degrees of freedom calculated, and your statistics is not anymore valid. I mean, it is not the same range. So what has been done is that, in terms of registration between subjects, the problem comes often with a non-rigid registration. I mean, in general, what is a non-rigid registration that has always failed according to the, depending on the size of the lesions. But this has been solved by, a linear scaling. A linear scaling adapted from the one hemisphere. From one hemisphere. One hemisphere that was okay. So it was. In any case, it was used to match all the subject in the MNI space with a linear transformation. Let's say, not rigid, but at least linear, just for scaling. Because since you have more or less the borders and the shape of the brain is usually, it does not fail, at least in the MNI space, to put all the subject in the MNI space. And then there is the other part of that, for statistical purposes, any voxel that was at least present in one lesion was removed from the analysis.
Thank you.